a mechanism of determining the stability of a system. And our earlier discussion, we talked about the root all-width stability criterion, where we're trying to look at filling the first column and checking the number of sign changes. If there are sign changes, then the system is unstable. If there is no sign change in the first column of the root all-width criterion, then we say the system is stable. So now we're also looking at another way of determining the stability of a system, using the Nyquist Stability criterion. And the Nyquist Stability criterion just talks about this one here in bold, that the number of encyclements about the critical point, is a critical point on the S-plane. I'm going to show you this one here, must be equal to the number of poles of the characteristic equation for the system to be stable. So I'll try to explain what is N. N is what you're calling the number of encyclements about the -1 plus J is 0. And then P is the number of poles in the right-hand plane for the open loop transfer function. And Z is the number of poles in the right-hand plane for the closed loop transfer function. So we want to illustrate this one here, just step by step. But the Nyquist stability criterion is just based on that argument about N being equal to P minus Z. So if this condition is met, then the system is said to be stable. But first of all, we need to do what we call a polar plot. So this is the most important part. You need to understand how you do a polar plot. And then once you do the polar plot, then you can go ahead to check the Nyquist criterion. So I'll just take you straight to the polar plot. The polar plot, you check two things. Number one, you check the phase, and you also check the magnitude. So if you have a complex number like Z is equals to X plus J, Y, then the phase is going to be the tan inverse, of that, of the Y component over the X component, and the magnitude will be the X squared plus Y squared square root. So that is how you are able to get that. And then, so once you have these two, you're going to do a plot of phase angle against magnitude as you vary angular frequency omega from 0 to infinity. So it should look something like this. So at the end of the day, we want to have a plot which looks like this. Maybe what I can mention at this point is that the phase angle will be changing either in the anti-clockwise direction or in the clockwise direction. If it is clockwise direction, it is negative. If it is anti-clockwise direction, it is assigned a positive value. So this is just an illustration of how you do the polar plot. For instance, here, these are values which have been populated. I'll show you how we are getting these values. But if we just check, for example, if the phase angle is -150, so that means we are moving in a clockwise direction. If we check out a -150, then the magnitude there will be 1.6. So just on that particular scale, you can be able to see there's a larger magnitude of 1.6. Then if now the phase is -160, so that means as the phase is increasing, the magnitude becomes 1. So here you can be able to see the angular frequency is also changing. But the key ones we are plotting is the phase angle and the magnitude. So let's just concentrate on these first two here. Then if the phase angle goes to 170, the magnitude is 0.6. If it goes to 180, so we have already done a complete change, 180 degrees. There, the magnitude, you can check on this arrow here, it is something like 0.4, the -190, we get 0.2. So if you join these points, like that, and you can even check the direction. So as the frequency is increasing, as you can see from this table here, then the angular frequency is also increasing. So once you join these points like that, and you indicate the direction, then you have a polar plot. So we'll do an example here where you check you're given a system here with a unit feedback. So we know how you can be able to, if it has a unit feedback, it means you can be able to visualize that block diagram, then where we have the unit feedback. A unit feedback is going to help us to be able to reduce an open loop transfer function to a closed loop transfer function. So if this is the open loop transfer function you are given, then using the Nyquist criterion, determine the system stability in a closed loop configuration. So I want to take us through this example here to show you how you can be able to use the Nyquist criterion to determine the system stability in the closed loop configuration. So the first step, it is to replace S with omega J. So this one will enable us to get now values of omega. And once we have values of omega, we can easily get the magnitude and the phase. So here we have J omega plus 1, then you have J omega plus 2. So the magnitude, we are just trying to get the magnitude to be given by 50. On the upper side, there is no values of S, so it just remains there. Then we have the coefficient of omega there, of J rather, it is omega. So it is omega squared plus 1 squared square root. Then from the second one here in brackets, you're going to have omega squared, that is the coefficient of J, plus 2 squared, which will give you 4. Then you again get the square root. So this value here, this equation here will give us the magnitude. And so remember, we shall be firing the magnitude and check how, angular frequency omega, and check how the magnitude will be changing. Then also look at the phase. So the phase here, the phase is basically the tan inverse. But since these values are on the denominator side, we use minus. So it is minus tan inverse of, for the first one here, we are using this equation. So it will be the tan inverse, the x value is 1, the y value is omega. So it is omega divided by 1, which is just omega. Then we have another one here. Our y value is omega, our x value is 2. So it is the negative tan inverse of omega divided by 2. So if we add these two values, they will give us the total phase, which we are going to use in plotting the graph. So we have tried to populate. You're going to draw a graph, a table like this one, which you're going to populate with values of magnitude and phase as omega is changing, as it is firing from 0 all the way to infinity. So we want to look at a number of cases here. When the omega is equals to 0, if omega is equals to 0, then it means this value will be 0 here. We'll have here square root 1, and then this value will be square root 4. So square root 1 is 1, square root 4 is 2. So the magnitude will be 50 divided by 2. So in the table here, we feel 25. What about the phase? For the phase here, we have our omega is equals to 0. So if definitely omega is 0, then this one will be 0, and this value will be 0 here. So we fill 0 in that column. Then we vary angular frequency. You can just pick any values here. So I've just picked the number of values here to show you how we populate this graph. So for example, if we have 1, if we place 1 here, our magnitude is going to be, so here we have a root 2, and here we have a root 5. So you want to have 50 divided by root 2 divided by root 5. So if you have your calc with you, can be able to check that one out. You should be able to get negative, rather 15.8. And then if you also check for the phase, negative tan inverse of 1, it is negative 45 degrees. Negative tan inverse of 0.5, it should be able to give you negative 26.56. So putting these two together, we have a total phase of negative 70. I can just check this another column here. If omega is equals to 10, for instance, if omega is equals to 10, then definitely we're going to have 101. You're going to have 104. So it is 50 divided by root 101, root multiplied by root 104. So if you do that with your calc, you should be able to get a magnitude of 0.5. And then if it is 10, the negative tan inverse of 10 plus the negative tan inverse of 5, should be able to get a value of negative 163. So if you have your calc with you, you can be able to check this value here. Maybe you can look at one more, because it's very important to understand how to fill this table. It is the backbone of our Nyquist criterion. You must be able to do the polar plot. So once more, if omega is equals to 20, so 20 squared is 400, so you're going to have root 401 here, and here we have root 404. So if you have 50 divided by root 101, is it 104? No, 401, 404. You should be able to check to get a magnitude of 0.1. And also, if you do the same here, negative tan inverse of 20 plus negative tan inverse of 10, omega divided by 2, should be able to get negative 171. So I believe I've shown you how you can be able to fill this table here. And it's very clear that as you're increasing omega, the magnitude is decreasing towards 0. And also now the phase will be kind of increasing in the clockwise direction to tending towards negative 180 degrees if you continue populating it out. So we now go ahead and try to plot our values. So we are plotting on the real axis. We plot the values of the phase, of the magnitude, and then you also now check, we can be able to check the phase. So for example, the first one, our phase is equals to 0. So that means just along the positive x-axis, it is just 0. And the magnitude for that point, it is 25. So you put that value there of 25. Then we increase the phase. We increase the phase to negative 72 rather. So just by approximation, because you're doing a sketch, it is somewhere there, 90. You also